Welcome everyone to our talk this afternoon about Auro Tripathy, marketing agile. We're going to deliver the talk titled "A Gentle Introduction to Sparsity with a Concrete." Auro is a machine learning model, and for the next 30 minutes, Auro, you have our attention. Thank you.
Hello, audience. I'm going to start. Okay, I'm going to roll.
Go ahead. Yes, we can hear you.
Okay, good. Thank you. So I'm going to roll. And the talk is really about sparsity. Before I start, I want to thank MLOps Toronto, Bay Area. I've been working with lots of people, Faraz, Jen, et cetera, to get this going. So thank you very much. And where I'd like to start is the state of machine learning, worldwide interest. So worldwide interest has been growing, of course, since 2014, where we had the advent of AlexNet, and it gave us 75% top 5 accuracy, and since then accuracy has been growing, but somewhere around February 25, interest waned a little bit. And this is, of course, the day when the World Health Organization, announced the onset of the pandemic. And since then, you might see that the interest has dropped a little bit. So with that in the backdrop, what happened? What happened is the human endeavor to better understand our world didn't skip a beat. In July of 2020, July 22nd of 2020, we got this paper called Language Models Are Few-Shot Learners. And with that came an explosion in model parameters. So we're now roughly at 175 billion parameters, which is 10x of the year before, which is Turing NLG, which is at 17 billion parameters. And imagine where we were in 2015, which is ResNet 50 was roughly 25 million parameters. So from 25 million parameters, we've had this journey in model parameter explosion. So we've gone from BERT-based uncased, which is about 110 million parameters, to larger and larger models. GPT-J is a very interesting model. It's about 6 billion parameters, and it's very comparable to others. And we'll be announcing some GPT-J inferencing on a single card fairly soon. But this is where we are in terms of model parameter explosion. And what have we accomplished through this model parameter explosion? What we've accomplished is we've gone from learning from millions of images to learning from very little sample data, few-shot learners. And with that model parameter growth, we've also had some staggering compute growth. And the metric that's most commonly used these days is called petaflops per second days, which is like kilowatt hours when you think about energy. It is a metric that's not just a compute metric like flops. It's a compute time product metric. So for instance, it takes 3,640 days in terms of if you think about it, roughly an 8x V100 class machine to train this level of models. And we, of course, know that for training something like ResNet 50, 8 V100s, MLPerf is roughly 30 minutes or so. So we're going from a 30, 45 minute convergence to top 5 79.5 accuracy. That level of convergence to now petaflop per second days, which is now 3,640. So this is to show you the explosion of compute. And by the way, this is a log scale, so every notch is 10x in scale. So with this, how are humans doing? We just need 12 to 20 watts to get through our day. All the decisions we make throughout our day, all of the things we recognize as we drive our cars on the road, in terms of pedestrians and sidewalks and traffic lights, and all of that decision making that we do just takes 12 to 20 watts, which is roughly the fifth of the power consumed by a 60-watt light bulb, right? And this is astounding, but I want to also give you some of the references to read up on it if you like. And the first one is from Scientific American, and that shows you how to compute, how to translate calories to watts, etc. So you'll get a feel for how much decision making, inferencing that the brain does at very little energy consumption. And how do we do that? We've heard a lot about spiking neural nets. That's how the brain works. It combines certain input and then generates a spike. And we're inspired by those models, whether they apply directly or not is we won't discuss that, but certainly the inspiration of spiking neural nets and sparsity comes from the brain. Okay, so moving along, now we're going to actually jump into the topic of sparse networks, because we have some mental models about how much compute, what's the model size. We've got some inspiration from the brain, and we'll now just define what is sparsity. And roughly, sparsity is nothing but the ability to zero out or prune or disconnect certain connections. So think of a weight matrix that is 4x4, and this is all fairly dense, meaning every neuron is connected to every other neuron. And this is a dense scenario where everything is connected to everything, and there is a non-zero weight associated with it. So that's dense connections. Now, these are 16 connections, so 4x4, 16 connections. And in this case, we're showing a sparse and wide connectivity. So we've got 8 inputs and 8 outputs, and the weight matrix is 8x8, but there's a preponderance of zeros. So we maintain those same 16 connections, but we zero out the rest. And in this case, we have a hidden layer in between. Well, these are all probably hidden layers, but we have deep layers, but we have the same number of connections, 16. And again, there's a preponderance of zeros. And we all, by now, if you've kept up with the literature, we know that bigger the model, better the results, less the number of samples we need, if we're fine-tuning, etc. So this kind of grounds us in what sparsity means. And all it means is we zero out a lot of connections. We have very sparse connections. Okay, so again, we going back to grounding ourselves. There's a very curious paper called the lottery ticket hypothesis, and I'm going to quote it and read it exactly the way it's stated in the paper, which is a randomly initialized dense neural net contains a subnet. It contains a subnet that is initialized such that when trained in isolation can match the test accuracy of the original network after training for at most the same number of iterations. Okay, so what's going on? We have perhaps a dense neural net here. It's fairly dense. Everything's connected to everything else, and we have some random weights. Uh, when you do weight initialization, that in and of itself is an art. So you must have heard of the He initialization. You have normal initializations. You have Gaussian distribution initializations. There are many ways to initialize, but pick your initialization, random initialization, and initialize your weights, and then train. Next, what you do is you do magnitude pruning of the weights. So you start pruning your weights, you pick a certain percent, and you say, below this threshold, I'm going to essentially zero out all the weights. And you remember that mask of what you zeroed out. And then you train again. And when you do train, you use the same initial random weights, and you apply the mask, of course. So if a certain weight you've already pruned out, you don't initialize that to zero. But other than that, you use the initial random weights, and you train again. And you can continue this process, and pretty soon you will be able to see the hypothesis work, which is we are able to match the test accuracy with these heavily pruned networks. Okay. So with that as a background, I want to come up with a fairly concrete example of that. And that is this network called Linnet 300. That's the name of the network. It uses the MNIST dataset, and it builds a digits classifier. And the digits are 0 through 9. It's not the classical convolutional ReLU max pool type network, but it's a fully connected network. So everything's connected to everything else. And we're doing this just to prove our point about sparsity. So you train this network, and here's the repo where you can get the PyTorch code, and it's built from another it's just a refactored version of the original repo that I've pointed you to there. But the idea is once you train, you get to a certain accuracy, 88.37%. This is with maintaining zero sparsity. You have all the weights. Okay, so you do this, and then you follow the hypothesis, which is you prune 75% and retrain with the initial random weights. Remember, that was the hypothesis. You have to go back and train with the initial random weights. And you have to apply the prune mask, of course, because whatever you decide to zero out based on your threshold, you zero out, and you'll see lots of zeros here. And you train this, and your training after pruning gets you the same accuracy, in this case, slightly better. And the paper also says that your network becomes a little more robust because of the sparsity. But we've kind of proven the hypothesis with a concrete example with a very simple MNIST data set and a Linnet 300/100 model. So the idea is you take the image, you flatten it out. That's 784. You fully connect with 300 hidden layers. You again fully connect with 100 hidden layers, and that's your score. So we've proved the hypothesis. I wanted to do that myself, and I wanted to share that with you as well, that this works. And look at what we've accomplished. We've essentially, if you look at the pre-train and the pre-prune and the post-prune, you'll see that behavior, that the loss is roughly the same, and the validation accuracy is roughly the same with the pre-prune network and the post-prune network. And this is also available in the repo, but there's many examples on the net of how to do this. So now we've talked about sparsity in the context of fully connected layers, and with all of the great uh, innovations happening in natural language processing, we want to stop by and talk about sparse attention. And or sparse transformers. The core building block of transformers is attention, of course, and this is really very simply exemplified here, and that is you have three inputs: the query, the keys, and the values. You take the scale dot product of the queries and the keys, you apply a softmax, and then you just do a multiply add with the values, and this is the core compute. But this compute is quadratic, is order n square. This compute is order n square because imagine a sentence you have maybe 30 or 100 tokens long. You're doing pairwise dot products. Since you're doing pairwise dot products, it's an order n square problem. But what sparse attention does is it really does what's limited, what's said here, which is you don't compute all the pairwise dot products. You limit the number of pairwise dot products, and you can do that randomly. You can do that with some heuristic that you want to apply. And then we've got we meaning Tenstorrent, we have a bunch of heuristics that we apply. But whether it's random or heuristical in nature, that gives us some great results through these nets: the sparse transformer, long former, routing transformers, reformers, and big bird. So all of these are examples of sparse attention and sparse transformers. Okay, so we've talked about fully connected sparsity, or introducing sparsity into fully connected models or connections. We talked about sparsity at the attention layer, and this is where you'll get the biggest bang. Maybe you'll get it in convolutional networks, maybe not. But these two certainly are candidates for sparsity because they have indeed taken the compute and made things order n square, etc. So finally, uh, this is my last slide where I want to kind of present what the Tenstorrent does. And that is, here's three, let's just take the example of matrix multiplies. So we have two inputs, the activations and the weights, and we're just going to do a simple matrix multiply. And this is the naive case, right? This is the order n cube case where you essentially, if you're doing batched matrix multiplies, etc., you'd end up with a huge amount of compute if your matrix sizes are big, and they could get very big in the case of natural language processing because your sentences, etc., could be long. The next one shows if you have some heuristics that you can apply during training or inference, doesn't matter. You can then and if your hardware is capable of certain kinds of uh, processing, then you can have the results very sparse. And this is linear speedup. Remember, if you go back to the example where we had 16 connections, the compute is proportional to the sparsity directly. If you pruned out 90%, then you have 90, you really have a 10x gain, and that's what we're showing here, that we get a speed of 10x with 90% sparsity in this type of a situation, provided you apply the right heuristics during training and your hardware is capable of detecting certain uh, detecting or enabling those heuristics rather. And then we can go to even higher levels, and we need them because our models are now 175 billion parameters, and we really need to take that compute down a notch or two. So the idea is here, your inputs can be sparse as well. So your activations are sparse, and with that, you can now get some much higher speed ups, 100x speed ups when you get to a 90% sparsity. um, so this is real. This is something that we need to do given where we are with the state of our parameter size, with the state of our compute. And that's where I want to end my talk and open it up for questions.
Okay, hi. Thank you so much, Aura. We really enjoyed the talk. That was a great delivery. And I will now welcome question from the participants. Kindly type in your question in the chat box, and I will relay it back to Aura.
So Franklin, should I do something to see the question on the chat box, or?
No, I will read it out to you. You don't need to say it. Okay, just
Thank you, thank you,
yeah.
thank you. Yeah,
If
thank you.
anyone asks question, I'll read it out to you. We're still waiting for the questions, all right. But in the meantime, if anyone wants to reach out to you, can you maybe share your email address or maybe your LinkedIn if someone wants to connect?
Absolutely. So I'm going to move away from this presentation and go to LinkedIn. Is that it?
No, don't worry. Just hold on a bit. We have a question. Someone asked a question now, so let me relay the question.
Yeah,
Uh,
please.
from JT Howe, it says, could weight matrix be less dense if not at all sparse? Did you get a question?
What I got was, could weight matrix be less dense?
If not at all sparse.
If not at all sparse. Yes, the weight matrix is essentially holding the pruned picture. So when you say less dense, it certainly could be 90% zeros. In fact, that is what we did in our experiment. In our experiment, we essentially masked out 75% of the weight matrix right here is what we did.
Okay, I think he's satisfied. He say thanks. Okay, I think you answered
Thank
the
you.
question. Yeah.
Thank you.
Okay. Okay. Then another question from John Scarlton.
Mhm.
He say, "Hi, Auro. Great talk. How much higher are the system requirements to make sparse calculations than the normal dense calculations?"
How much higher are the system requirements in order to do the sparse calculations as opposed to the dense calculations?
Yeah.
Did I repeat that correctly?
Yes, you're right.
Okay, thank you. All right, so yes, the trick is what heuristics you apply. So assume we're training, right? When we're training, we want to do less number of calculations. We can do the naive set of the naive approach, which is we use the entire activation weight matrix and compute. But the trick is to have some very light heuristics that will tell you which parts to not compute. And this can be done various ways. It can be done at the block level, which we do. If you look at some of our competitors, they do it at the row level. So they're able to very quickly determine what not to compute during training, during inference, doesn't matter. But the trick, that's the trick, is so there's a little extra work you have to do, but that extra work should be so low compared to doing the entire dense calculation that it's meaningful to have you quickly decide, okay, these specific blocks we don't need to compute, and we can essentially get by with the rest of the blocks, and we just proceed with the rest of the blocks. So yes, there is a little extra work, but it cannot be so much that it is the penalty is so high that you might as well do the entire naive compute.
Okay. Thank you. Okay. I think if he's satisfied, say thank you.
Thank you.
Hopefully we get more questions. Yeah, and as one of your colleagues has shared your email, so you don't need to share it again. Eric has shared your emails to the chat. So I will still have like 4 minutes. Do you want to add anything while we wait for the questions?
I want to thank the audience. I want to thank you guys. Yeah, I don't have more to add. If anybody wants a conversation with Tenstorrent, I would encourage them to come and go to the website, of course, enter your interest, and we're getting ready to launch our stack in 4 to 6 weeks, where we will be able to walk you through some examples. GPT-J, of course, is something that we're working on very hard that we'll be able to share with you. It's a much smaller model, but it's comparable to much larger models. So it's kind of the right model to be working with, et cetera. So yeah, that's all I want to share. Yeah, please get in touch if there's interest.
Thank you so much, Auro. And thank you everyone for joining us for this talk this afternoon, stroke morning. If you're from the West Coast, hopefully we'll get to see some other time, and we'll now officially close the talk. Have a nice day.